On the 13th of April, 2026, Geely revealed a number that grabbed the attention of the automotive industry: 48.41%. To most people, it looked like another statistic. To engineers, it seemed impossible, because every time a car burns fuel, most of that energy never reaches the wheels. It escapes through the exhaust, gets absorbed by the engine, and disappears as heat. For more than a century, engineers have tried to reduce those losses, but every improvement became harder than the last. By the early 2020s, many believed they were running out of room. When Toyota reached 41% thermal efficiency, it was celebrated as one of the greatest achievements in modern engine design. Then Geely announced 48.41%. And suddenly a settled question was open again. What if the limit wasn't a limit at all? Behind that question was something much bigger than one engine. A billion-dollar race over fuel efficiency, regulation, manufacturing, and the future of the global car market. Before we can understand how Geely got there, we need to understand why so many people believed it could not be done. If you're new here, stick around. This is the kind of story that doesn't make headlines, but changes industries. Why 40% was supposed to be the wall. Before Geely put 48.41% on the screen, the number everyone in the industry respected was Toyota's 41%. And this was not some fragile prototype hidden in a lab. It was tied to Toyota's 2.5-liter dynamic force engine, the one used in mass-market cars like the Toyota Camry and Toyota RAV4. Toyota said this engine family could reach around 40% thermal efficiency in gasoline form and about 41% in hybrid vehicles. In other words, one of the world's most efficient combustion engines was sitting inside cars ordinary people could actually buy. For the old automotive powers, that felt like a final answer. Not just a technical answer, but a business one, the kind that shaped product planning, factory investment, emissions targets, and hybrid strategy. Because for more than a century, the gasoline engine had been fighting the same enemy: waste. A car engine takes fuel, sets it on fire, creates a tiny explosion, and tries to turn that explosion into motion. Simple enough. But most of the energy inside gasoline never reaches the wheels. It escapes through the exhaust, leaks into the metal, and disappears as heat. Engineers spent generations shrinking that loss. They improved fuel injection, valve timing, friction, combustion chambers, and airflow until engine design started to look less like machinery and more like controlling a tiny storm. But the closer they got to 40%, the harder every improvement became. Make combustion hotter, and you extract more energy but risk damaging the engine. Increase compression, and efficiency improves, but the fuel can ignite too early. Reduce friction, and you save energy, but durability becomes the next problem. So 40% was never a magical limit, it was a practical wall. And when Toyota reached 41%, it did not feel like a beginning. It felt like the ceiling had finally been measured. But when that ceiling finally cracked, it did not happen in Germany, Japan, or America. It happened in China, a country the old automotive powers had long treated as a follower, not the one that would redraw the limits of combustion engineering. The first warning shot nobody took seriously. The first crack in the wall did not come from Geely. It came from BYD. In 2024, BYD put its fifth-generation DMI plug-in hybrid system into two ordinary-looking sedans, the Chin LDMI and the Seal 6 decimeters I. These were not supercars. They were not concept cars. They were affordable family sedans built for the mass market. And inside them was a number the rest of the industry could not ignore: 46.06%. That was the claimed thermal efficiency of BYD's new hybrid engine platform. And while 46.06% may not sound dramatic to most people, in combustion engineering, it was a warning shot. The cars also arrived with headline figures. Fuel consumption as low as 2.9 liters per 100 kilometers when the battery was depleted, and a combined range of around 2,100 kilometers on a full tank and full charge. Those numbers mattered because fuel economy affects ownership cost, fuel spending, emissions compliance, oil demand, and the billion-dollar strategy of every automaker in the energy transition. But the real story was the idea behind it. For decades, hybrids worked by letting the gasoline engine and electric motor share the job of moving the car. Sometimes the motor helped, sometimes the engine took over, sometimes both worked together. Because a gasoline engine only works at its best in a narrow sweet spot, and real driving almost never lets it stay there. Hills, traffic lights, acceleration, braking, every change pulls it away from the place where it burns fuel most efficiently. BYD asked a sharper question. What if the engine stopped chasing the road? For most of the journey, The wheels could be driven by electric motors, while the gasoline engine stayed in its most efficient zone and generated electricity. Instead of reacting to every hill, every light, and every press of the accelerator, the engine could stay where it worked best. That is why 46.06% mattered. BYD was not just improving the engine, it was changing its role. And while the industry was still trying to explain that away as a China-only story, Geely was preparing something even more extreme, something that would make BYD's 46% look less like the finish line and more like the first warning shot. The tornado inside the engine. This is where Geely breaks the rules, because the jump to 48.41% did not come from making the engine slightly lighter or shaving off a little more friction. Geely Auto went straight into the place where combustion efficiency is really won or lost: the cylinder. This technology sits at the heart of Geely's new i-HEV intelligent hybrid system, demonstrated in a Geely M-Grand and planned for models like the Preface, Manjaro, and Starray. This was not just a lab experiment. Geely was building it for real cars, real buyers, real regulations, and a real fight for hybrid market share. Inside the cylinder, the problem is simple. Air and fuel do not naturally mix perfectly. Think of pouring cream into coffee without stirring it. Some areas become cloudy, some stay dark. Inside an engine, that uneven mixture creates pockets where there is too much fuel, and others where there is too much air. So when the spark plug fires, the flame does not burn everything at once. It starts in one spot, then moves across the chamber, slowly. And while that flame is still moving, heat is already leaking into the metal walls. Energy that should push the piston down is being lost before the engine can use it. That is one reason traditional engines struggle to move beyond the 40% range. Geely's answer was the Yufeng tornado combustion system, or more simply, a fire tornado inside the engine. Instead of letting air drift into the cylinder, Geely redesigned the intake channels so the air enters in a high-speed spin. A controlled vortex forms before ignition, mixing air and fuel far more evenly. So, when the spark fires, the flame does not crawl across the chamber. It spreads fast, clean, almost all at once. More force goes down onto the piston. Less heat leaks into the walls. Less fuel is wasted. In a global industry where every fraction of a percent can affect fuel economy ratings, emission scores, pricing, and compliance, that is not a small gain. But this creates a new danger: knock. Push combustion too hard and the engine starts fighting back. Geely's fire tornado solved the first half of the problem. The second half was even smarter, building an engine that could handle the storm. The engine that runs hot and cold at the same time. This is where Geely had to solve the problem every combustion engineer fears. Heat. Push combustion harder, and the engine becomes more efficient. The explosion gets hotter, the pressure rises. More force hits the piston. More energy comes out of every drop of fuel. But push too far, and the engine starts to turn against itself. The fuel can ignite before the spark plug fires. That is engine knock, not just a rough sound, but a violent shock inside the cylinder. The kind that can damage pistons, crack components, and turn a breakthrough into an expensive warranty problem. That is why the 41% wall lasted so long. Engineers knew how to make combustion stronger. The hard part was keeping the engine alive. Geely's answer was to stop treating the engine as one temperature problem. In a normal car, coolant flows through the whole engine and tries to keep everything at one safe temperature. It is a compromise. Good enough for ordinary engines, but not good enough for this. Because the top and bottom of an engine do not need the same thing. At the top is the cylinder head, where the explosions happen. This is where heat appears first. This is where knock begins. So Geely keeps this area aggressively cold, pulling heat away before the fuel can ignite too early. That colder top section keeps the air charge dense and stable, allowing a much higher compression ratio than usual. Higher compression means more pressure, more force on the piston, and more efficiency. But lower down, inside the engine block, the fight is friction. So Geely keeps this lower section deliberately warm. Warm oil flows more easily, becomes thinner, and lets the pistons move with less resistance. That means less energy wasted as metal grinds against metal. It also protects durability in mass production, because a breakthrough only matters if it survives real roads, real customers, and real service costs. So the top stays cold to stop knock. The bottom stays warm to cut friction. Two opposite goals, one engine. Geely split the cooling system into separate zones and used an electronic water pump to adjust coolant flow in real time. The engine stays cold where heat is dangerous and warm where heat helps. Geely did not accept the old compromise. They rebuilt it. And even then, the engine was only half the story. That energy still had to reach the wheels without getting lost in the gearbox. If you're enjoying this breakdown, hit like and subscribe, because next, we're going from the engine to the system that decides where all that power goes. Throwing the gearbox in the trash, Geely had already won the battle inside the cylinder. The fire tornado made combustion faster. The split cooling system kept the engine alive. More energy was being pulled from every drop of fuel than almost anyone thought possible. But that energy still had to survive one more journey, from the engine to the wheels. And in most conventional vehicles, that journey runs through one of the heaviest, most complicated parts of the entire vehicle, the gearbox. A traditional automatic transmission is an incredible machine. It shifts smoothly, handles torque, climbs hills, and works for years. But it is also a maze of metal and friction, gears, clutches, shafts, hydraulic fluid, torque converters, and hundreds of parts moving together just to transfer power. Some energy becomes motion, some becomes heat, some gets swallowed by friction before it ever reaches the road. So even a 48% efficient engine does not mean much if the gearbox quietly bleeds away part of the gain. That is the problem Geely wanted to avoid. Toyota had already changed the hybrid world with its e-CVT system. In the late 1990s, it was revolutionary. But more than 25 years later, Geely saw something still tied to the old mechanical age. Clever, proven, but still full of places where energy could disappear. So Geely started over. What they built is called the 1-1-in-1 EDHT intelligent drive system. But calling it a gearbox almost misses the point. It is really an energy router. Inside one compact unit, Geely packed the engine, the generator, 2 electric motors, high-voltage control hardware, and thermal management. Instead of forcing power through a long mechanical chain, the system chooses the cleanest path for energy in real time. For about 90% of daily driving, the gasoline engine is not physically connected to the wheels at all. It runs at its most efficient speed and powers a generator. That electricity either charges the battery or goes straight to the motor driving the car. From behind the wheel, it feels almost electric, quiet, smooth, instant. The engine is still there, but it is no longer chasing every hill, every red light, every movement of your foot. It has one job: run where it works best. But at steady highway speeds, especially around 80 miles per hour and above, the system changes strategy. Sending power through electric motors can waste more energy than a direct mechanical link. So the car locks the engine to the axle, like a top gear, and sends power straight to the wheels. Then AI manages the whole thing. 50 times every second, it decides where energy should go. It can read the route ahead, see a hill coming, and choose whether to charge the battery, use electric power, or save energy for the descent. This is not just mechanical engineering anymore. It is software, power electronics, route prediction, battery management, and real-time energy optimization in one powertrain. Put everything together: the fire tornado combustion, the hot and cold engine, the 1-1-in-1 drive unit, and AI power routing, and you get the number that makes this system feel almost impossible. 2.22 liters per 100 kilometers, and more than 2,000 kilometers on a full tank. In a world where fuel prices, emissions rules, charging infrastructure, and electric vehicle adoption all vary from country to country, numbers like this are not just engineering claims, they are market weapons. At that point, this is not just a better hybrid, it is a different way of thinking about how a car should move. What this means beyond the car industry. At first glance, this story looks like it's about an engine. It isn't. For years, the global automotive industry operated under a powerful assumption. The future belonged to battery electric vehicles, and the internal combustion engine had little left to offer. That assumption shaped government policies, corporate strategies, supply chains, and investment decisions worth hundreds of billions of dollars. And to be clear, electric vehicles remain one of the most important technologies of the 21st century. They are efficient, increasingly affordable, and in many parts of the world, they are already the right solution. But technological progress rarely follows a straight line. History is filled with examples of industries declaring a technology mature, only to discover that a breakthrough was still waiting around the corner. That is why Geely's achievement matters. Not because it proves electric vehicles are wrong, and not because hybrids will dominate forever. It matters because it reminds us how dangerous assumptions can be. While much of the world was focused on replacing the combustion engine, engineers in China kept asking, what if the engine still had more to give? The answer appears to be yes. For consumers, it means more choices. For governments, more flexibility during the energy transition. For automakers, competition is far from over. For investors, suppliers, battery companies, oil markets, charging networks, and entire national auto industries, it means the future of mobility may be less predictable and far more competitive than the clean EV versus gasoline narrative suggested. Europe refined combustion. Japan perfected it. America helped build the industry around it. Now, some of the biggest breakthroughs are coming from a different place. China is no longer simply adopting automotive technology. It is increasingly helping define where that technology goes next. Whether Geely's 48.41% thermal efficiency becomes the start of a new chapter or simply an impressive milestone remains to be seen. But one thing is clear, the conversation has changed. Combustion technology has proven it can still move forward. Now the real uncertainty is who responds next. Before we end, there are 3 lessons here. First, never confuse a temporary limit with a permanent one. Second, breakthroughs often come from rethinking old problems. And third, the most dangerous words in any industry are, "That's as far as it can go," because sooner or later, someone proves them wrong. As impressive as 48.41% may sound, this story was never really about a single number. It was about a technology many people believed had already reached its limits. For years, the assumption was simple. The future belonged to electric vehicles, and the internal combustion engine had little left to offer. Geely's breakthrough doesn't necessarily prove that assumption wrong. But it does prove one thing. Innovation is rarely finished when we think it is. Whether ultra-efficient hybrids become a major part of the future or simply a stepping stone toward full electrification remains to be seen. But the race is far from over. If this video changed the way you think about where the automotive industry is heading, hit subscribe and turn on notifications. We cover stories that don't always trend, but quietly shape the future. Do you think hybrid technology still has a major role to play, or will EVs eventually dominate the road ahead? I want to hear your take, because this debate is only getting bigger. Drop your comment down below. Thanks for watching, and see you in the next video.